Our lesson today is lesson number 2 on permutations and combinations. You'll find this lesson on page 381 in your book. Today we're going to talk about something called factorial notation. So the example is, consider how many ways there are of arranging 6 different books side by side on a shelf. Using the fundamental counting principle that we learned about yesterday, we would calculate this product by figuring out that in the first position we could have any of the 6 books, then next we could have any of the 5 books that are left, any of the 4 books that are left, any of the 3 that are left, any of the 2 that are left, and for the last position on the shelf there would just be 1 book left. Okay? There is a simplified way to write this product, 6 times 5 times 4 times 3 times 2 times 1, when every number is just 1 less than the number before it, and it goes all the way down to 1. It's called factorial notation. And this same equation here, this same product, can be written as 6 factorial. 6 with an exclamation point. And that means 6 times 5 times 4 times 3 times 2 times 1. And it always ends at 1. Okay? Without using a calculator then, let's try A and see if we can figure out the value of 4 factorial. Well, that would just mean 4 times 1 less, 3 times 1 less, 2 times 1 less, 1, and you end at 1. Okay, so 4 times 3 is 12, times 2 is 24, times 1 is still 24. Okay, in this case we've got 3 factorial times 2 factorial. So first we do 3 factorial, which is 3 times 2 times 1. We'll put a bracket around that because that's 3 factorial. And then we're going to times that by 2 factorial, which is 2 times 1. Okay, so really it's 3 times 2 times 1 times 2 times 1. So 3 times 2 is 6, times 1 is 6. And 2 times 1 is 2, so 6 times 2 is 12. Okay, now, this is interesting to note. There are several different ways that you can write 6 factorial. Okay, 6 factorial means 6 times 5 times 4 times 3 times 2 times 1. But as you're doing that product, you can actually stop at any point along the way and leave the last number as factorial, like in this second one. 6 times 5 times 4 times 3 times 2 factorial. So that really means 2 factorial is 2 times 1, right? So that really means the same thing as this one did, right? Same thing here. If you wanted to end at 3 factorial, it really means times 2 times 1. So it really is the same thing as the original. If you ended at 4 factorial, 6 times 5 times 4 factorial, 4 factorial means 4 times 3 times 2 times 1. So that is the same thing as your original was, right? So at any point when you are expanding a factorial, you can stop at any particular number and just say factorial, and it means it keeps going and keeps going down to 1. You'll see why that's important in a minute. It comes into play when you are simplifying factorials and putting them in the simplified form, like in the next example here. In this example, we have a quotient. We have 6 factorial divided by 4 factorial. So what we do is we start expanding the numerator, and we stop it when we get to a number that equals our denominator. Okay, so in this case our denominator is 4 factorial. So when I'm expanding 6 factorial, I expanded 6 times 5 times 4, but I want to stop there because my denominator is 4 factorial. Okay, so I could just say times 4 and then factorial, which means it does keep going. And the beautiful thing about that is then this 4 factorial cancels this 4 factorial, and you're left with a quotient of just 6 times 5 in the numerator, which equals 30. Now the reason that that works is because of this. 6 factorial really means 6 times 5 times 4 times 3 times 2 times 1 in the numerator. In the denominator, it means 4 factorial, which is 4 times 3 times 2 times 1, right? Now, this 4, factor of 4, would cancel this factor of 4. This factor of 3 would cancel this factor of 3. This factor of 2 cancels this factor of 2. This 1 cancels this 1. So really, you are left with 6 times 5 in the numerator, which is what we had right there. Okay, so that's why this works. So when you are expanding a factorial, you expand the numerator until you get to the number that you have in the denominator and leave it as a factorial to show that it really does continue on like it did here. It does continue on with times 3 times 2 times 1. But those things from 4 times 3 times 2 times 1, those whole parts are going to cancel each other out, aren't they? So you're just left with 6 times 5 in the numerator. All right, so let's see if we can try B. B says express 5 factorial as a product in 4 different ways. Okay, well let's start with the original, which would be 5 times 4 times 3 times 2 times 1. Okay. Now, if I wanted to write 5 factorial in a different way, I just start 5 times 4 times 3 times 2 times 1, and instead maybe I'll stop at 2 this time. So 5 times 4 times 3 times 2, and then I can't forget to put factorial, which means it really is times 1 as well, right? Because they have to be the same thing. Okay, this one, I'm going to try, this time I'll stop at 3. So 5 times 4 times 3 factorial, which means times 2 times 1, right? And the last one, I'm going to stop at 4 this time. 5 times 4 factorial, which really means times 3 times 2 times 1. All right, C, complete the following. 12 factorial really means the same thing as what times 11 factorial? Right, 12 times 11 factorial, the factorial sign means times 10, times 9, times 8, times 7, times 6, times 5, times 4, times 3, times 2, times 1. It always will end at 1. Okay, 8 factorial means, well, we're stopping at 6 factorial, so it must be 8 times 7 times 6 factorial. Goes on and on. Okay, expressed as a quotient of factorials. 6 times 5 times 4. 6 times 5 times 4. Well, what I notice is missing from this one is times 3 times 2 times 1. So that's actually 3 factorial. So that would be in my denominator. So then on the top, I would have 6 factorial, because it's going to go 6 times 5 times 4 times 3 factorial. I'll write that so you can see that. So on the top, I've really got 6 times 5 times 4 times 3, and I'll leave that as 3 factorial, because on the bottom I have 3 factorial, right? And then my 3 factorial here and my 3 factorial here will cancel, and I'll be left with 6 times 5 times 4, which is what I wanted to be left with. All right, let's try number 2. 15 times 14 times 13 times 12. Well, what's missing is times 11 times 10 times 9. So my denominator must be the 11 factorial, which takes care of all of 11 times 10 times 9 and on, down to 1. And so on top, I must have 15 factorial, because once it gets to 11 factorial, the 11 and 11 on the denominator and the 11 factorial in the numerator are going to cancel each other out, just like they did in this question right here, right? Okay, without using a calculator, let's see if we can simplify these. So 10 factorial. Remember, if I'm expanding it, I'm only going to expand it as far as 7 factorial, then I'm going to stop. So this means 10 times 9 times 8 times 7, and then I have to remember to put my factorial sign to show that it keeps going down to 1, over 7 factorial. And what's going to happen is this will cancel this, and I'll be left with just 10 times 9 times 8, which, let's see, 10 times 9 is 90, times 8 is 720. All right, let's try this one. 8 factorial over 5 factorial, 3 factorial. Okay, well, 8 factorial, I'm going to keep expanding it until I get to 5 factorial. Okay, I could choose either one of these two denominators. I could expand it till it gets to 3 factorial, but it's going to be easier, since I can't use a calculator, to multiply 3 factorial times something than 5 factorial. So I'm going to go with my bigger one right now, because that'll cancel more out. Okay, so on the top I'm going to have 8 times 7 times 6 times 5, leave that as 5 factorial to show that it continues going, times 4 times 3 times 2 times 1. On the bottom I've got a 5 factorial. Those two are going to cancel each other out, but then I still have this 3 factorial, so I still have times 3 times 2 times 1. So what's going to happen here is this 5 factorial cancels this 5 factorial, and then I have, oh, look at this, 3 times 2, that's going to cancel this 6, right? So really all I'm left with on the top is 8 times 7, and on the bottom I've got over 1. So I've got 56 over 1, which is just 56. Kind of cool how factorials work, isn't it? They're really fun once you get the hang of them. Okay, so in general, this is how factorial notation works. So when you see n factorial, what that means is n times 1 less than n, times 2 less than n, times 3 less than n, and then it keeps going on and on and on forever till it ends at 1. Okay, where n has to be a natural number, like we're talking counting numbers. Okay, that's 1, 2, 3, 4, 5. Okay, not 0, because if n was 0, this whole thing would be equal to 0, because 0 times anything is 0, right? So counting numbers, natural numbers are not 0, they're counting numbers. And so n's are counting numbers, natural numbers, okay? So if you're going to expand an equation that instead of having numbers in it has variables like n, this is how you expand it right here. Okay, so n factorial is, it can be written many different ways, just like 6 factorial. It could be written as 6 times 5 times 4 times 3 times 2 times 1. Or you could truncate it and go 6 times 5 times 4 factorial, and that meant that it kept going on. It's the same thing when you're dealing with variables. N factorial means n times 1 less than n factorial. So that means it keeps going on and on and on until it gets to 1. Or you can go a step further and you can say n factorial also means n times 1 less than n times 2 less than n factorial. So it keeps going on and on and on until it gets to 1. Or n factorial is n times 1 less than n times 2 less than n times 3 less than n factorial. And on it goes. Okay? So let's see if we can try this time where some variables are involved. Okay? So n factorial means what times 1 less than n? Right, n. Yeah. Okay, b. n plus 2, how would you expand that? Well, we start with the number we have right here, so this is n plus 2. What would be 1 less than that? N plus 1, right. And then 1 less than that? N. And then we have the factorial sign to show that it keeps going and keeps going until it reaches 1. Okay, in this one, we've got n minus 4 times n minus 5 times n minus 6, dot, 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 and it ends at 1. So this is really how you would write n minus 4 factorial, right? Because you've got n minus 4, then n minus 1 more, then n minus 2 more, then it keeps going until we reach 1. Okay, that's n minus 4 factorial. Okay, so class example number 2, we have to simplify some expressions that involve n factorials and leave the answer in product form wherever we can. Okay, so it's the same rule of thumb as before. We're going to expand our numerator and keep expanding it until it matches our denominator. Once it does, we'll have values that can cancel out in the numerator and denominator, and we'll be left with our answer. Okay, so n plus 2. Well, n plus 2, 1 less than that is n plus 1. 1 less than that is n. And that's, oops, and that we're going to leave as n factorial. Okay, now that matches the denominator that I have, n factorial. So my n factorial on top and my n factorial on the bottom cancel each other out. And I'm left with n plus 2 times n plus 1. When it said leave it as a product, this is what it means. Don't multiply it out. We don't have to FOIL it to figure out what n plus 2 times n plus 1 is. That is our final answer. Okay, let's try B. We have n minus 2 on the top, and we have to keep expanding that until it matches our denominator on the bottom. Okay, you always expand whichever one is the bigger one. You expand it till it reaches the smaller one. Sometimes you'll find your bigger one is on the denominator in the bottom. So that's the one you would expand. The larger value is the one you start by expanding. This actually, in this case, which one is bigger? N minus 2, that means like 2 less than n, or the denominator, which is 1 less than n. Right, this is one of those cases where your denominator is larger. So it's actually the denominator you're going to expand till it reaches the smaller value, which is your numerator. So n minus 1 is our denominator. We're going to expand that one because it's the larger value. What's 1 less than that? N minus 2. Oh, now it matches our top number in our numerator. So we're going to leave it as n minus 2 factorial to show that it keeps going and keeps going till it reaches 1. In the numerator, we have n minus 2 factorial. So what happens here is your numerator and denominator n minus 2 factors cancel each other out, and you are left with nothing on top? Oh no, that's not nothing. Right, that's 1 over n minus 1 on the bottom. All right, let's have a look at this one. Which value is greater, n or n minus 1? Right, n factorial is greater, isn't it? Okay, so we're going to factor that. N factorial on the top is n times n minus 1 times n minus 2, and it keeps going on and on and on, so we'll put the factorial to show that it keeps going on and on and on. Then on the bottom I have n times n minus 1. In this case, my n's cancel, my n minus 1's cancel. You can see why I had to keep expanding it even beyond when it reached n minus 1, because I had to have an answer. Otherwise, I would have had like nothing left. Everything would have canceled each other out. So I need to have an answer, which in this case is n minus 2 factorial is left. All right, class example number 3, algebraically solve this equation. Now, up until now, all of these questions that we've been working on, it's just been asking us to simplify it, leave it in simplest form, okay? In this case, when we have an equal sign in the middle, it's asking us to find out what the value of n is. We need to end up with an expression that says n equals some value, okay? But we do it the exact same way. We're going to simplify the expression on the left until whichever is the greater value, we're going to simplify it until it reaches the same value as the lower value, and then they will cancel out and we'll be left with n equals something. Okay, so when you look at your numerator and your denominator, which value is greater, n factorial or 2 less than n factorial? Right, n factorial is greater, so the top is what you're going to start expanding. So n times, what's 1 less than n? Right, n minus 1. What's 2 less than n? N minus 2. And we're going to leave that factorial because now it will match the n minus 2 on the bottom. Okay, n minus 2 factorial will cancel n minus 2 factorial. So then we know that we've gone far enough. Now don't forget, you have the other side of your equation, which still equals 42. Okay, so what I'm left with now, and you can see this is just going to be an easy algebra to solve, I'm left with n times n minus 1 equals 42. Okay, now using regular algebra now, I'm going to multiply this n times n minus 1, so I've got n squared minus n equals 42. Now I need to bring everything over to the left-hand side so that because I have an n squared, and so it's going to be a quadratic equation I'm going to have to factor. So n squared minus n, I'm going to subtract 42 from both sides, equals 0. Now I just factor it like usual because I'm trying to solve for n. So I'm looking for two numbers that will multiply to give me negative 42, add together to give me negative n. Right, that's going to be a positive 6 and a negative 7. Okay, so I set both factors equal to 0. If n plus 6 equals 0, then n is equal to negative 6. Or if n minus 7 is equal to 0, then n equals 7. Okay, well now I have to go back to my original equation and see which one of these could actually be true, because remember we had talked about the fact that in this equation, right up here at the top of the page, if you look back here, in the definition of n factorial, n has to be a natural number, a counting number, 1, 2, 3, 4, 5, 6, that kind of a number. So in this case, n equals negative 6 would be rejected as an answer because n cannot be n factorial. You can't take the factorial of a negative number. Okay, let's make ourselves a note here. Okay, at the top of your page, can't take the factorial of a negative number. Something important to remember. So when you get two answers, n can't be both of them, and so you'll have to check your answers and see which one would work in the situation. And you can't say negative 6 factorial because you can't take the factorial of a negative number. And so n factorial would have to be 7 factorial over 5 factorial equals 42 is what your equation then would say if you plugged your n value of 7 in. Okay. You can check that on your calculator. You can see if 7 is n, then 7, that means 7 factorial over, and you'd have 7 minus 2, which is 5 factorial, would equal 42. Let's see if it does. 7 factorial would be 7 times 6 times 5 factorial. Oh, I don't have to go any further because I've got 5 factorial in the bottom. Equals 42. This 5 cancels that 5. 7 times 6 is 42. So in fact, 42 equals 42. So you've just verified your solution. Okay, so that's how you can check it. Okay, let's flip over the page, and I'm going to show you that on your calculator you have a factorial button where your calculator will do some of this work for you. Okay. Okay, so the question says, use the factorial key on the calculator to evaluate the following. So instead of having to figure out 6 times 5 times 4 times 3 times 2 times 1, or plug all that into your calculator, you can go into your factorial button, which if you go into your math button, go across the top to probability. You see number 4 shows the factorial sign, so you hit number 4. Okay, so to start, if you were doing 6 factorial, you would hit 6 and then do math across the top to probability, number 4 for factorial, and hit enter. 6 factorial is 720. Simplifies things a little bit. 9 factorial, so plug in 9, go to math, across the top to probability, down to number 4, 9 factorial, enter, 362,880. Okay, now to simplify a quantity like this quotient, 10 factorial over 7 factorial times 3 factorial on a calculator, we can evaluate the numerator and the denominator separately and then divide, or it is possible to actually enter the whole thing into your calculator as long as you use brackets. Okay, so in this case they've figured out what 10 factorial is, then they figured out what 7 factorial was, and then they figured out separately what 3 factorial was and multiplied them together, and that's how they got this denominator of 30,240. When you divide that, you get 120. But a simpler way to do that, and to allow your calculator to do all the work for you, is just go 10 factorial and then make sure that you put divided by and use brackets. So bracket 7 factorial and 3 factorial, exactly like it is in the book. Make sure you close your bracket so that it's seeing this whole 7 factorial times 3 factorial as one value, so you bracket it, okay? And then when you hit enter, it gives you the same answer we came up with when we did it. Numerator and then denominator and then divided. So you can do it either way, whichever way you prefer. Now, to verify without using a calculator, complete the work below. Okay, so 10 times 9 times 8 times 7 factorial over 7 factorial times 6. Well, we know the 7 factorial will cancel the 7 factorial. And so what we'll really have is 10 times 9 times 8. Well, 9 times 8 is 72, times 10 is 720 over 6. And if you divide 720 by 6, you have 120. Okay, so this is just showing another way. If you didn't want to do that same question this way, by figuring out your denominator and your numerator separately and then dividing, or you didn't want to do it this way where you just plug it all into your calculator using brackets, you actually can expand your top, expand your bottom, and see what cancels and come to the answer that way as well. It's just a third way to do it. Okay, and knowing how to do all 3 ways does come in very handy depending on the question that you're solving. Okay, so class example number 4 says calculate the value of 43 factorial over 40 factorial. Well, when you can allow the calculator to do the work for you, why wouldn't you? So 43 factorial divided by 40 factorial. I must have hit a wrong button here. Let's try that again. There we go. Okay, and it's 74,046. Okay, Try the next one, stop the video, and then start the video again and check your answer. Okay, I hope you were able to get 66,045 as your answer. Okay, now as you can see, there are some questions that go along with this to practice simplifying factorials and solving factorials equations. And so I'm going to have you work on 1 to 6 at the end of class, but we are going to continue on and do this next section as well, which is permutations. And then you'll have a chance to do all of those questions at the end of class, okay? Okay, so remember yesterday when we were learning about the fundamental counting principle, I said that permutations is another way that you can figure out the number of different arrangements of objects that when order does matter. Okay, so you're going to need a highlighter. We're going to highlight some kind of important information in this. The first example says, an internet site's access code consists of 3 digits. Knowing the 3 digits is not enough to access the site. The digits have to be entered in the correct order. The order of the arrangement of the digits is important. Highlight that sentence. Whenever a question is asking how many ways could you arrange something, if they use that word arrangement or arrange, it indicates that order is important. So you're going to be using permutations. Okay? Now, in this situation, John can't remember the access code except that it contains 3, 5, and 7. Those are the digits it contains. Okay, so we need to figure out all the different arrangements of these 3 digits that John could use to determine his access code. Okay, well, we know it could be 3, 5, 7, or it could be 3, 7, 5, or if it didn't start with 3, maybe it started with 5, 5, 3, 7, or 5, 7, 3, or maybe it didn't start with 5, maybe it started with 7, 3, 5, or 7, 5, 3. So there are actually 6 possible arrangements to consider, and only one of them will actually access the site. This type of arrangement, where order does matter, order is important, is called a permutation. Again, let's highlight that because this we need to get really, really clear in our head. When we are arranging objects and order is important, it's called a permutation. And again, the definition is important as well to highlight. So a permutation is an arrangement of a set of elements in which the order of those elements is important. Okay, so list all of the different arrangements. We're talking about some arranging items that indicates order is important in the letters of the word cat. How many different ways can we arrange the C, the A, and the T? Now, in this case, it means we're using all 3 letters. We have 3 letters available to us, but we're using all 3 of them, right? It doesn't say how many different arrangements of 2 letters in the word cat can you make. It's saying list all the arrangements of the letters in the word cat. So could be C-A-T, could be C-T-A, could be A-T-C, could be A-C-T, could be T-A-C, could be T-C-A. Okay? When you are arranging letters or numbers, order is important, okay? Because C-A-T is not the same thing as A-C-T. They contain the same letters, but the arrangement, the order, is important. Okay, so how could I write how many permutations, different arrangements of these letters, did we make? If I was writing this in factorial notation. How many different ways can you arrange 3 letters? You can arrange them in 3 factorial different ways. What that really means, and we know now, that means 3 times 2 times 1 different ways. How many is that? 3 times 2 is 6, times 1 is 6. So 3 factorial is 6. And this is how many different ways we could arrange those 3 letters, okay? So when you are using all of the letters in a word, or all of the numbers that you're given, then you can write it as a factorial to arrange those letters, okay? So this is the general rule. The number of permutations of a certain number of different elements, if you take all of them, taken all at a time, is n factorial. Okay, so how many ways can you arrange 7 different letters? It would be 7 factorial. How many different ways can you arrange 3 letters? 3 factorial. How many different ways can you arrange 12 different letters? 12 factorial. Okay? Okay, so let's try class example number 5 then. How many different permutations, order matters, that's what that word says to me, order matters. How many different permutations of the letters of each word can you make? So, Regina. Now I have to use all the letters. So how many letters are there? 1, 2, 3, 4, 5, 6 letters. So I can arrange 6 letters in 6 factorial different ways, which is, if you plug that in on your calculator, 720. Right. Okay. How many different permutations can I make of the letters in the word Kelowna? 1, 2, 3, 4, 5, 6, 7. 7 factorial different arrangements of those 7 letters. So if you plug that into your calculator, that's 5,040 different arrangements of the letters in the word Kelowna. Okay, so this is the general rule when you are using all of the letters that are available to you. Okay, now this example here is we're making arrangements again of so many different elements, but this time we're not using them all. We're taking some at a time, okay? So we might be just arranging 3 of the letters in a great big long word, okay? Or 5 of the letters in the word Regina instead of all 6, okay? So in that case, we can use the fundamental counting principle to determine how many 3-letter arrangements can be made. From the letters in the word graphite. Okay, so how many letters are there in the word graphite? 1, 2, 3, 4, 5, 6, 7, 8 letters in the word graphite. Okay, and this time I'm making a 3-letter arrangement, so that means I'm going to have 3 letters in this word. How many letters do I have available for that I could put in this first spot? Right, any of the 8 letters. Okay, now if I've used one of the letters, I can't repeat it because I'm using each one of these letters in this word graphite, right? I don't have other letters available to me. I don't have 2 G's or 2 H's. I have just 1 H, 1 G, right? So I have to only use the letters in this word. Okay, so I'd have 8 available to me in the first, for the first letter in this word, but then I'd have 7 available to me that I could use for the next letter, and I'd have 6 available to me that I could use for the last letter. So I have 336 different 3-letter arrangements I could make from the letters in the word graphite. Okay, now the way that we would write this in permutation, as a permutation instead of in fundamental counting principle, would be this way. Okay, when I'm arranging a certain number of letters or numbers or people where order does matter, it's written this way. Out of 8 letters in the word, I am arranging 3 of them. Okay, and the P denotes it's a permutation because order matters. Okay. Now what 8P3 actually means is 8 times 7 times 6. It means what we just did here, okay? And the reason is because if you kept expanding it, it's 8 times 7 times 6 times 5 factorial, so it keeps going, all over 5 factorial. And this would cancel this, and you'd be left with 8 times 7 times 6 on the top, which is 8 factorial, all over 8 minus 3 factorial. Now, all that to say, don't worry about that. They're just showing you that because they're showing you where this formula comes from. Okay, this is the general rule for figuring out the number of permutations, the number of arrangements where order matters, of a certain number of elements if you only take so many at a time instead of all of them. Okay, so this is the formula. Out of so many elements, if you're only taking a certain number at a time, it's the total number of elements, factorial, over this minus this, factorial. Okay, so left to right, it's just like it is in here. It's this minus this, factorial. Okay, now there is a button on your calculator that will do this. Okay, so once again, when you go in to your math, go across to probability, and you'll see down here, number 2 is NPR. Okay, that's the button we're going to use. But first, we have to go back out, because if we were trying to evaluate 8P3, we have to put the 8 in first. So you go 8, then you go math, over to probability, go down to number 2, and now it says 8 NPR 3 equals. Okay, and it will tell you what 8 NPR or 8P3 really means. Okay, so this means you're doing permutations where out of 8 objects you're choosing to arrange 3 of them. Okay, so there's, on our calculator we did 8P3, that was 336. Now this question has asked us to go a little further because now they want us to verify our answer. In other words, prove that the answer is right by using factorials. Okay, so what that really means is 8P3 means I have 8 factorial on top, because that's my, if I'm looking at this equation here, that's my n, right? N is how many I'm choosing from altogether, over, and then here it's this number minus this number. So 8 minus 3 factorial, which is, oops, 8 minus 3 in brackets factorial. So that's 8 factorial over 8 minus 3 is 5 factorial. Where if I expanded that, that's 8 times 7 times 6 times 5, and I leave it there because it matches my 5 factorial on the bottom now. And this will cancel this, and I'll be left with 8 times 7 times 6, which is 336. Okay, so we've verified it, we've proved it using the formula. This formula will be on your formula sheet for any exams and for the diploma. You don't have to memorize it, but it is an important one to know and to know how to use. All right, the next page says, well, if you can't take the factorial of a negative number, can you take the factorial of 0? And the answer is yes. And the only thing you really need to know about that, and I'd like you just to highlight this, you really don't need to know how or why, although I'll show you in a minute, but the value of 0 factorial is 1. Okay, 0 factorial equals 1. Okay, so you can't take the factorial of a negative number, but you can take the factorial of 0, and it is 1. And the reason for that is, if you took that equation that we just were working with, what that's saying is, if I'm arranging a permutation, an arrangement of a certain number of elements, and I'm using all of those elements, that is, to arrange them, it's that number of elements factorial. Okay? So back to the equation, it would be n factorial on the top, the total number of arrangements, over this minus this, which is n minus n factorial, which is 0 on the bottom, and n factorial has to equal n factorial, so that number on the bottom, 0 factorial, must equal 1, because n factorial over 1 is the only way you're going to get that, right? So they're just showing you the proof here. What you really need to understand and what you need to remember is that 0 factorial does have a value of 1. Okay, a license plate question again. in a region, vehicle license plates consist of 2 different letters followed by 4 different digits. If the letters I, O, Y, and Z are not used, determine how many different license plates are possible using the fundamental counting principle. Okay, well, how many spots are there in this license plate? It says it consists of 2 different letters followed by 4 different digits. So there's 6. 1, 2, 3, 4, 5, 6. Okay. Now it says 2 different letters, but we cannot use I, O, Y, and Z. So if there's 26 letters in the alphabet and 4 of them we can't use, that means we have 22 left that could be used in this first position, and then 21 left that could be used in the second position. Okay? Because it says they have to be 2 different letters. So I can't use the same letter in the second spot that I used in the first spot. Okay, no repetition. Okay, then I have to have 4 different digits, and there are no restrictions on those digits. So how many digits are there? Right, there are 10. So I could put any of those 10 here. Then they have to be different digits. So if I've used a digit here, I can't use it again. So now there's only 9 choices left, 8 choices left, 7 choices left. Okay, and this equals 2,328,480 different license plates I could make. Okay, I figured it out using the fundamental counting principle. I also could figure it out using permutations. Okay. Okay, so first of all, I'm going to have to figure out the 2 different letters, how many different options there are to arrange those 2 different letters. Okay, so let's see, that's a permutation because order matters. I'm arranging letters. Okay, I have 22 available to me that I can choose from because I can't use these 4, right? So just like here, I only had 22 I could choose from. Okay, and I am choosing to arrange 2 of them. Okay, and, okay, this is not an or, this is an and, so times. And I'm also having to arrange 4 different digits. So I've got a choice of how many digits? 10, and I am choosing to arrange 4 of them. Okay, so 22p2 times 10p4. And if I do that on my calculator, let's see if we can get our calculators to do this. So we have to plug in the 22, then math button, go over to probability, go to number 2, 22p2. Oh, I forgot to put my bracket in. That's okay. Remember, you can insert, whoops, second value and insert. If this is going to let me do it on this board. Oh. It might not. I'm going to just clear it and start again. You can insert. It's just being finicky on the board today. Okay, 22. Oh, I did it again. Sorry, let's put in the bracket. Okay, 22. Math. Permutations of 2 objects. Bracket times bracket. 10 permutations of 10, or of 4 objects equals 2,328,480, which is the exact same thing we got here. Okay. Okay. So you can do when you have an arrangement where order does matter, you can either use the fundamental counting principle to figure it out or permutations. Just remember, like we learned the other day, where if you are arranging this and you are arranging this, you need to make sure you have times, because when it's this and this, you multiply the number of ways that you could arrange the letters with the number of ways you could arrange the digits. Okay, and our last one today says algebraically solve the equation n minus 1 p2 equals 90. Okay, well, algebraically means I need to go back to my original equation, my permutation equation, and set it up. So I know that that equation is NPR equals n factorial over n minus r factorial. Okay, so my n is how many things I'm arranging. Well, in this case, it's n minus 1 things that I'm arranging. Okay, so that's going to be my n minus 1 factorial. Okay, and then on the bottom, in my numerator, it's that minus that, right? So I've got n minus 1 minus 2 factorial. And I guess this would be in a bracket because it's all of that factorial. Okay, so then I'm going to be expanding this, what I have in the denominator, so I'm just going to leave my numerator exactly like it is, because on the denominator now I've got n minus 1 minus 2, which is really n minus 3 factorial. Okay, so now I'm going to do some expanding, and I need to figure out if it's going to be my numerator or my denominator that I'm expanding. Remember, it's the larger value that you expand until you get to the smaller value. So let's see, I've got 1 less than n on the top, and I've got 3 less than n on the bottom. So my 1 less than n is greater. So that's the one I'm going to expand. N minus 1, 1 less than that's n minus 2, 1 less than that's n minus 3. I'm going to stop there, so I'm going to show that it keeps going on, though, with a factorial sign. N minus 3 factorial on the bottom. This n minus 3 factorial will cancel this one. So on the top, I will just be left with, or in total, I will just be left with n minus 1 times n minus 2. Okay, so this is my final answer, and that's how I would leave it. I would not expand it and FOIL. I would leave it that way. Now, this actually was just this, I have just figured out this side. That has to equal 90, right? So what I really have is n minus 1 times n minus 2 has to equal 90. Okay, now in this case, if I were just leaving it as a simplified factorial, if this was all the question had asked me, then I would just leave it in this form. But because I do have to actually solve this equation and come up with n equals something, I am going to have to FOIL this now that it's in the equation form. So I have n squared minus 2n minus 1n is minus 3n. Negative 1 times negative 2 is positive 2. And that equals 90. So then I'm factoring this, looking for 2. Oh. Sorry, nope, I'm getting ahead of myself. I can't factor that yet. I have to bring that 90 over, don't I? Sorry, I was getting too excited to start factoring. Okay, so I'm going to subtract 90 from both sides. So I've got n squared minus 3n. Subtract 90 from both sides, so 2 minus 90 is negative 88 equals 0. Okay, I'm looking for two numbers that will multiply to give me negative 88, and they will add together to give me negative 3. Now I can factor. I love factoring. Well, the only numbers I know that multiply to give me 88 would be 11 times 8. There's a difference of 3 between those. It must be negative 11 and positive 8. So that tells me n is either 11 or n is negative 8. Okay, well, going back to my original equation, I've got in the numerator I know that my n cannot be negative numbers, and so I'm going to reject the negative 8 and know that my n has to be 11 because n has to be a natural number, a counting number. And in any equation, n factorial over n minus r factorial, your n has to be a natural number, counting number, so it can't be a negative. Okay, so I know my answer is n equals 11. Okay, so I think the practice on these skills is very important. I would really like you to do all of the questions in this assignment. So that's questions 1 to 15, so that you have the practice and feel confident with these.